This PowerPoint video is going to be on section 6.4 and 6.5. So we start off with 6.4. We're going to investigate the effect of changing temperatures on the volume that the gas occupies. So the first gas law we're going to look at is called Charles' law. And in Charles' law here, we're starting off with a piston in a cylinder with a gas trapped in here. And the gas is creating pressure by bouncing off the walls of the container, and it's keeping the piston pretty much at a steady spot here. And the temperature is 200 Kelvin. Make sure you have the temperature in Kelvin now. And the volume, let's say the volume is 1 liter. And so what happens is we're going to increase the temperature to go 400 Kelvin. So we're doubling the Kelvin temperature. Now, if you change these Kelvin temperatures to centigrade, you wouldn't be doubling them at all. So you must make sure you have the temperature in Kelvin when you work with Charles' law. So what happens when we double the Kelvin temperature? The volume doubles, because now the particles are moving faster because we heated the container, and because they're moving faster, they're bouncing off the walls of the container harder and more often, and that pushes up on the cylinder. So the volume increased. And this is the gas law right down here. V1 over T1 equals V2 over T2. So it's a direct proportion. As temperature goes up, so does the volume. Now let's take a look at Charles' law a little bit closer. And so here's, I mentioned before, V1 over T1 equals V2 over T2. Most of the time you're going to be asked to find what's the new volume. So if we take our ratio, if we cross multiplied it, we'd wind up with this on top. And then we'd be dividing both sides by T1 so that you get V2 by itself. So when we do that, the T1 would cancel out. And that's why we're left with this expression here. So that's the way we're going to be solving ratios. Cross multiply and then divide. So let's see if you can do that for Charles' law. Now you want to solve for T2. So start off with the ratio and see if you can solve the expression for T2. And then we'll take a look at the answer. Okay, the answer for this one, we start off at the top and they put T2 in a different color to make it easy. We cross multiply. We wind up with this then. Now we have to divide by V1 to get T2 by itself. And see the V1s would cancel out, and then we're left with what we need. And then we can plug our values in and make sure that the volumes will cancel. So that must have the same unit. So here's an example now. The balloon has a volume of, I'm going to underline the data, 750 ml. So that's going to be V1 at 21 centigrade. Okay, so we measure things in centigrade. That's T1. And you notice right away they changed it to Kelvin. You want to do that right away because you probably will forget, and that messes everything up. If the temperature drops to 0 centigrade, what will the new volume be? So now they changed the 0 centigrade to 273 Kelvin. So our unknown is V2. So if we wanted to solve this then, we would take our formula and we would cross multiply and divide. We'll wind up with V2 equals this. And then we could plug our data in, canceling out the Kelvin temperatures. And we get this for a volume. Now let's check to make sure it makes sense. So if the temperature goes down, then the volume should go down. So I write that. So if T decreases, then the volume will also decrease. We can see this exactly what happened. Here's one for you to try. We have a sample of oxygen gas at a volume of 420 ml at 18 centigrade. What temperature in centigrade will the volume be at 640 ml? Now you notice it says what temperature in centigrade. You still solve the problem for Kelvin. Then after you solve the problem for Kelvin, then you convert to centigrade. Okay, why don't you give it a try. Alright, here's the solution. We copy out the data and label it, so you can see we're looking for T2. Notice that the 18 degrees centigrade is changed to Kelvin right away. Now before we go any further, let's predict what T2 will be compared to T1. What's happening to the volume? If the volume goes up, then the temperature should go up. That means T2 has to be bigger than 291 Kelvin. So we take our formula, we rearrange it for T2. We plug in our values, we cancel out the milliliters. Get this moving here. and we get 443 Kelvin. So 443 Kelvin because the volume went up, the temperature must go up, and that's exactly what we got. All right, so here's some other questions for you to answer. So read through these, and then when you have your answers written down, then go to the next slide to see what it is. Right, so here are the answers. The pressure increases when the volume decreases. When the temperature decreases, the volume decreases. So the first one, that's Boyle's law. That's an inverse relationship. The second one, that's Charles' law. That's a direct relationship. And let us see, the pressure decreases when the volume changes from 12 liters to 24 liters. Again, that's Boyle's law. So the pressure goes down when the volume goes up. And then for D, the volume increases when the temperature increases. Okay, not too bad. All right, the second one we're going to go over today then is the relationship between temperature and pressure. And this should be kind of common sense as well. So Gay-Lussac's law is what we're going to be checking out today. So we start off with that same piston and a cylinder setup where the piston can rise or fall. Now we heat the piston and the cylinder, but what happens is the piston is as high as it can go. So in a sense, we have a container whose volume is not going to change. So if the volume can change and you heat the container, what happens? Well, the particles move a lot faster. They bounce off the walls of the container a lot harder and more often. And because the piston can't move, the pressure goes up. And if you look down here now, 200 Kelvin becomes 400 Kelvin, and the pressure went from 1 to 2 atmospheres. So this is a direct relationship between pressure and temperature. But again, the temp must be in Kelvin. And there's our gas law right over here. This is the law of Gay-Lussac. So again, we have a direct proportion. And so if you're asked, solve this formula for P2. So we're going to cross multiply, and then we're going to isolate P2. So we start off with the gas law. So we cross multiply, and this is what you get when you cross multiply. And then we're going to divide by P2 on both sides. And then we wind up with this. So it's always cross multiply first and then divide. All right, here's an example question. A gas has a pressure of 2 atmospheres at 18 centigrade. What's the new pressure when the temperature is 62 centigrade? So the temperature is going up, and so the pressure will go up. Here's our data. Notice how we're changing temperatures to Kelvin. Okay, we're going to write our gas law. Here's our gas law here. We cross multiply and then we divide. They're not showing you the cross multiplying here, but that's what you have to do. And then we substitute our values in, and you notice we had the pressure going up. Exactly what we thought would happen. Now here's one for you to try. A gas has a pressure of 645 torr at 128 centigrade. Where torr is a unit of pressure. What's the temperature in Celsius if the pressure increases to 824 torr? So remember, do the problem in Kelvin and convert it to Celsius at the end. All right, why don't you pause the video and try to answer the problem. Okay, here's the solution. Copy out the data and label it, changing our temperatures to Kelvin. Write our formula down, cross multiply, and divide, and we get T2 equals this expression. Plug our pressures in, cancel out the units, do the math, we get 512 Kelvin. But remember the problem said, what is it in Celsius? So we have to convert back to Celsius. And there we go. Now the vapor pressure, which is the pressure of a vapor above its own liquid, like water vapor above water. If you have a little water bottle there in front of you, above the liquid water in the bottle, there's water vapor. And that vapor creates a pressure. So that's what they're talking about with vapor pressure. Now the pressure of that vapor increases as you heat that liquid. And once you reach a pressure that's equal to the atmospheric pressure, then the liquid can actually boil. So we actually define boiling point as a temperature at which the vapor pressure, the pressure above its own liquid, is equal to the atmospheric pressure. So let's check it out now. So here we have a diagram where we have some boiling water. Yeah, we have a thermometer in here, and you see it's 100 centigrade. That's a normal boiling point. Now it says the atmospheric pressure is 760 millimeters. So this is done at sea level. So this is the pressure pushing down. The pressure of the bubbles of vapor is also 760. So this is what they mean by the boiling point. Now what would happen if this pressure, the air pressure, was less? Well, then the liquid would be boiling at a lower temperature because the pressure here could be less. And that's what this table is showing us here. So as the temperature increases, the vapor pressure increases. Now this might refer to more like about using, well, let's say you're in Denver and you want to make some hot water, boil water. What happens if you're in Denver and you're heating water? Well, the air pressure in Denver is less than normal. Let's say it's only 752 millimeters of mercury. That means that the boiling point will be less than normal. Now, you would notice a difference like this is only 1 degree. But if it was that much smaller, which it wouldn't be, then you might start to notice it. And then we have the opposite. You notice I mentioned a pressure cooker. A pressure cooker actually works by trapping the water inside in a closed container, and then you heat that container, and there's a small amount of water in it, and that water will start to boil. But when it boils, it creates its own vapor, and eventually the pressure of that vapor becomes greater than normal. Let's say it could come up to maybe this inside the pressure cooker. And what does that mean? That means that the liquid that's inside the pressure cooker can also be at a higher temperature, like 120 degrees. So pressure cookers, which were really big in the 1950s, really shortened the cooking time for many different foods. For instance, you can boil a chicken so that the meat falls off the bones in only 15 minutes in a pressure cooker. Whereas if you were doing that in a pot on the stove, it would take you well over an hour. Right, so question, explain why water boils at a lower temperature in the mountains than at sea level. Well, what do you think? Well, the answer is, of course, the atmospheric pressure of the mountains is less than at sea level, so therefore the vapor pressure of the water reaches the atmospheric pressure at a lower temperature. So like in Denver, if you're heating water in Denver, the pressure of the bubbles of vapor that you're creating will equal the pressure outside at a lower temperature, so the water is lower. So this also means you can control the boiling points of liquids. Okay, and that's the end of the show.